Hello everyone. Big audience. Okay, so today we're going to talk about performance in web applications, and this talk is a bit front-end focused, but at least I have my Java shirt on. Okay, so my name is Sebastian Springer. I'm here from Munich and I work as a JavaScript developer. And I hope I can tell you something new about how to speed up your stuff in the web. And the reason why I've chosen this engine thing here is that the core internals of the Chrome browser are named after motor parts, so it's kind of connection. So the first step in speeding up your application might be optimize your own code. So try to make your script stuff a little bit faster, because that's the most obvious thing. So unfortunately, I have only a little bit of JavaScript code. So let's look at this. This is micro-optimization in JavaScript. So the first code block is a regular loop over an array with 3 items in it. And the second one is a little bit optimized, which gives us 0.something milliseconds, which is not that much. We get this optimization by caching the array length in a variable, so we don't have to look up the length of the array, but only to get to the memory where we stored it previously. So this brings us some split milliseconds. And now we have a look at what our engine, so the heart of our browser, does to the code. So remember this, some 0.something milliseconds, and this is what the browser does to our code. And this gives us 1.something milliseconds, which is a lot more than our own optimization. So what do we learn of this? Don't optimize your code, because this is not readable. No one sees the difference between the first and the second one. And if you write your application clever, then the engine of your browser is able to optimize your code a lot better than you can do it on your own. And we will come back to this example later on, and I'll explain you how to get this performance boost. So what to learn of that example? Don't do your own optimizations, because that's kind of stupid, because if you optimize your code, it reduces readability. Write clean code, write readable code, and let the engine of your browser do the rest of the thing, and keep the big picture of your application in mind and not the fancy stuff which doesn't bring you anything. So what's interesting for us? It's very simple. The time until the user can interact with our application. This is the first and the key metric of the performance of our application. And this is tightly coupled to a thing called the critical rendering path. So the most important thing is, how long does it take for our users to interact with our application? And then further on, how long do the interactions take? And this first part of the performance figure of our application has to do with HTML for the structure, with CSS for the good-looking part, and JavaScript for the logic in the front end. So if you want to measure the time of the critical rendering path, the starting point is this. So the user has his browser open and hits in a URL in the address line. And then, in the worst part, the user waits some time. A good measurement for the user waiting is a couple of 100 milliseconds up to 1 or 2 seconds. If your application takes longer than 1 or 2 seconds to load, then you've got a problem, because your users don't want to wait. So if you're interested in how long your page takes until it's loaded, just open the DevTools of your browser and look at the tiny red number on the bottom of your page, and this is the time the page takes to load. And you have to reduce that. So the big players, such as Google, are investing a lot of money to reduce the time the user until the user interacts with the page. Because if it takes too long, the user walks away and never comes back. So what are the parts of this critical rendering path? So from this to that, your browser has to do a lot of work. It has to process the HTML structure. It has to process the CSS structure. It has to create a mixture of HTML and CSS, and it has to display all the things. And until point 4, your browser does not display anything but a white page, which is not that good. So the first step is the processing of HTML, and the people of Google wrote a very, very good documentation about how the browser performs this step. And this image is directly taken out of this documentation because it just shows you how the browser works. The browser gets some bytes from the server. Then it transfers the bytes into characters, which is plain text HTML, but the browser does not show the plain HTML, but transforms it into tokens, which are specified by the HTML standard. These tokens are enriched with further information and transformed into nodes. And those nodes are building the document object model, which is a tree structure. And here you see an example of such a tree structure with one root node and several child nodes. Next step, our browser shows a white page until that. The browser has to do the same for CSS, because CSS is for the good-looking part, so it doesn't make any sense to display a raw HTML structure because that looks shitty. So processing CSS takes the same steps: bytes, characters, tokens, nodes, and then the object model, in this case not the document object model, but the CSS object model. And the two tree structures, the HTML for the structure and the CSS, are merged together into a thing called render tree. And this render tree consists of all the visible parts of your application. So if you hide some nodes by CSS, they are getting kicked out and not rendered in the browser. How you can measure the building of those structures, it's fairly simple. Just open the DevTools of your browser and go to the timeline, and then you see what your browser does under the hood. The browser takes 60 milliseconds for loading all the stuff. Then it does a lot of scripting, which is JavaScript. Then it renders, builds up the trees, and then it paints the trees. And the rendering process is the building of the trees, and then the browser tries to put the elements into the correct place and displays it to the user. And here you can clearly see where to optimize. So the problem is not the painting or the rendering, but the scripting part. And this is one of the most important things. Know where your problems are. So if you start optimizing the painting portion of the critical rendering path, it doesn't make any sense because you only have 2.3 milliseconds. You cannot even optimize that much so that it makes any difference. But here in the scripting part, which takes 400 milliseconds, there is a big potential for improving the performance of our application. And you have a lot of tools which help you even more in measuring your application. For example, there is a tool provided by Google which is named Lighthouse, and that breaks it down even more and gives you more metrics on your application. For example, the performance part of the measurements, which tell you how long does it take until the user sees something. In our example, it's 1.1 second. And this is the user sees something of your page. So not a white page, but something where the user can look at. And it takes 3.9 seconds until the user can completely interact with our application. So there are certain steps in the process, and yeah, the first 2 parts are green, so it's okay, and the time to interact is fairly long, which is 3.9 seconds, and this is orange, so you should take care of this number. This tool is available as a browser plugin, so you can easily install it in your browser and then just use it on your own application, and your application doesn't have to be in the internet, but in your own intranet, so you can even measure your company internal applications with that tool. So you remember this one, and the first part of the critical rendering part is the loading section, so the blue one, which is in this case not that much. But the first part of the process we have a closer look at. The browser receives the URL of our application, and then it goes to the server and asks the server, "Dear server, please give me the resources I need to display the page." And the problem with the downloading of resources is that the browser has a limited capacity of parallel connections to the server. These are example figures, so Firefox and Chrome are able to process 6 parallel requests, and if you have a 7th or 8th request, they are queued until one slot gets free and then the rest is downloaded. If you think of the building of the structures, you have the HTML structure and you have the CSS structure. If you reference some CSS files in your HTML, then it downloads the resources and waits until the resources are available, and then it continues to render the tree. So if you put in 15 or 16 CSS resources, you block yourself, because you only have 6 parallel slots to download the stuff, and then it just waits for the next slot to be available, and the rendering is delayed even more. So use as few resources as you can, because that doesn't block the browser. How can you further improve the downloading figures of your application? You can use several tools, for example, minifier that strip away unnecessary characters. For example, documentation or comments. You don't need, or the browser doesn't need any comments in the code because it doesn't read them. So it strips away the comments, and you can do it for the browser on the server side and reduce the amount of data that gets transferred over the line. The browser doesn't even need line breaks or unnecessary white spaces, such as multiple spaces or something, because the browser doesn't care. So you can minify the sources of your application and that gives you 50 to, let's say, 80% of a reduction of the source code, because there are a lot of unnecessary stuff in the files. For example, if you have a variable name called hello world, the browser doesn't care if it's hello world or just a. So this JavaScript minifiers, for example, take long variable names and shorten them up consistently over the application and reduce the amount of data that gets transferred over the line. The same is true for CSS. There, the unnecessary white spaces and comments and stuff like that are stripped away. And you can even improve the loading time of your images if you put them together in just one big file and then use CSS to only show a certain part of this big picture. This is called CSS sprites, and there are a lot of tools that help you in generating those sprites and generate the necessary CSS for that. So you don't have to take care of that on your own, but let the tools do it for you. If you want to measure the download performance, so to figure out where your problems are, just use the DevTools of your browser, and then you see a figure like that. This means that the download of a certain resource can be split up into various sections. In this example, you have the connection setup, which is, for example, the SSL handshake, which takes a certain amount of time, or then the request response phase of the download, or the request download. You have to send the request to the server, which takes 0.11 milliseconds in our case. Then the server has to process the request, which takes time. If the green bar is big, then you know you have to either insert a cache or improve the performance of your server. If the blue part of the download split up is big, then you know you are transferring too much data over the line. This is the content download. This is from starting from the browser receives the first byte until the download is complete. And yeah, the green bar gets reduced by improving the server. The blue part is reduced by reducing the size of the download or improving the speed of the connection. How can you further improve this this figure here? Either by including some caches, either server side, so you take out the server portion of the game, or you can use the browser cache. So use HTTP headers to tell the browser, dear browser, please save certain files in your cache and use the cached version of the file and not the server version of the file. And recently there was a new technology introduced in the meantime all of the browsers, which is called service workers. And this is a client-side proxy server which is able to intercept server calls and deliver a locally stored version of a certain resource directly in your browser. So your request doesn't leave the browser but is answered directly in the browser, which is pretty cool. And more applications are set up on the base of service workers, which are transparent to your client-side application. So if you don't have service worker support, for example, in an older Internet Explorer browser or an older version of Chrome, it doesn't matter, because the proxy is placed between the browser and the server on the edge of the browser. So if it's there, it's used, and if it's not there, the requests are redirected directly to the server and it doesn't care, or your browser doesn't care. You can use your DevTools in order to maintain the service workers and have a look at the status of your service workers, and you can start or stop or reload the service worker and do a little maintenance. And you can even have a look at which kind of service workers are registered in your browser by hitting Chrome service worker internals or something, and then you get a list of all the installed service workers in your browser. And it's kind of interesting which pages are using service workers. Angular.io, for example, is using service workers. And a lot of magazines and stuff like that are using service workers too in order to improve the speed of the page. I already told you that CSS is blocking the rendering part of the critical rendering path because it doesn't make any sense to show unstyled HTML. So in order to speed up the rendering path of your application, reduce the amount of CSS you're using in your application. The lesser CSS and the lesser HTML you use in your application, the faster the process of the rendering is. Do not use CSS imports because a CSS import is referencing a further resource of CSS in your style sheet. And what your browser does is it sees this add import statement and goes to the server and tells the server, please give me the next resource, blocks the rendering process even more, and waits until the stuff is there. Then it continues to build up the CSS object model, and the rendering is delayed even more. So use as few HTML and CSS as possible, and the same is true for JavaScript. If your browser hits a script tag, then it downloads the resource and blocks the rendering process. So be very, very careful where you include the JavaScript of your application, and because that is also blocking the rendering process. Because the browser hits the script tag, then it processes the whole JavaScript of your application, and then it continues. And why is that the case? Because JavaScript is able to influence the document object model. So you can change the structure of your document object model, and the browser does not render until this process is complete, because that would result in some strange behavior, because if you remove a certain part of your application or the DOM, then it has to re-render. And in order to skip that, the browser waits until the process is complete. And there exists an architecture to overcome this problem, which is known as the app shell architecture, which is a minimal version of your application, minimal version of HTML, minimal version of CSS, and minimum JavaScript. And all the rest of your application is loaded afterwards, asynchronously. So you give your users a small part of your application in order to play around with it, and while the user has a look at your application or this part of your application, you continue to load resources from the server and then build up the rest of the application. Because what does your user see on the first glance? Everything that gets displayed on the screen. Everything out of the screen the user does not see. So you can focus on the part of the application on screen and build up the rest of the application later on, which is a dirty trick, but it works pretty well. So this is the critical rendering path. This is the process from a blank page until the page gets fully displayed to the user. And as soon as the application is displayed, another part of the life cycle of your application starts. And this is where it's getting interesting for us, because if you have a single page application, you don't have that many requests or page loads, but you have the centerpiece of your application, and then you take parts of your application out and replace them with dynamically generated content. And there are other rules for this part of the life cycle which don't apply to the critical rendering part or the first render step of your application. The big chance and the big problem of a single-page application or an application that is loaded in your browser is that the page is open in the browser and you don't have any reloads. What is the big advantage of a reload? The memory gets cleared and everything is cleaned up. So unnecessary JavaScript or parts of the DOM tree that are not needed anymore are just kicked out. And in a single-page application, you don't have any reloads, but your application stays open for a couple of hours. Advantage, your application state is stored in the memory, and memory access is much faster than a request over the network. The objects are stored in the memory, so you have to clean them up and do a little bit of housekeeping in order to keep the memory clean. If you don't do so, you end up in a memory leak and your browser is consuming more and more memory, up to a few gigabytes, and then your system gets slower and slower, and then the user is forced to reload the page and then drop the state of your application out of the memory. The advantage of a single-page application, which with the state stored in the memory, is that optimizations of the browser are getting more and more interesting for us. And this is where the JavaScript engines and the rest of the browser's engines are kicking in. You don't have a big advantage of an optimized JavaScript engine on the first page load, because the engine doesn't know of your application and how the users are using your application. But if your users are using the applications over a longer period, the engine gets to know the application better and knows which objects are reused and which objects are not reused, and is able to perform a lot of optimizations. And these optimizations are brought up by a competition of the major 4 browser creators, which are Google, Mozilla, Microsoft, and Apple. They are creating various JavaScript engines and rendering engines, and which are used to build up web applications. And the major 4 JavaScript engines are the V8, which is used in Node.js and the Chrome browser, the Monkey family of Firefox, Chakra of not the Internet Explorer but Edge, and the Nitro engine of Safari. We are focusing for this example on the V8 engine because it's very, very good documented, and the other engines are just working in the same way, or kind of the same way. So I'll show you a few optimizations of this JavaScript engine in order to let you know how to implement the front-end logic of your application in order to get optimized by the browser. One major feature of a JavaScript engine is, or one major feature of the V8 engine is the creation of hidden classes. And this is necessary because what do you do in JavaScript? You access objects, properties and methods of objects. And you do this very, very often in the life cycle of your application. And this has a very big potential for optimizations. Traditionally, you have a big dictionary where all the objects and the properties are registered. And if you access a certain property, then the browser's engine is looking up the location in the memory of this property, and it gets the content of this property out of the memory. Under the hood, all the objects are just object structures, and you can use a kind of class-based structure in JavaScript, which is known as the prototype style of JavaScript, because JavaScript is not class-oriented, but prototype-oriented. So you have a constructor function, which is in my case this point function. And in this point function, in the constructor, you can access properties. And if you do so, the engine does some work for you. So we start in the constructing of a new point. The engine creates a new hidden class for this point object. And then you call this x equals x, so you create a new property, and as soon as you do so, a new hidden class is generated, and the location of the x property is stored in reference to the class of this point. So you don't have a big dictionary, but a small dictionary for this particular object. Next step is access the next property, and then you have a transition from class 0 to class 1 to class 2, and class 2 knows where x and y are stored. This is a relatively slow process in the first step. So you create a new object and access the properties, and then the classes are built. This is an optimization that is kicking in when you reuse objects. So for all further access operations on this object, you can reuse this class C2, and the property access is very fast. And the big advantage is if you reuse this class or the prototype of the point, then those transitions from these classes are reused. So you build up this structure once and then reuse them. So if you run your application over a longer period, at some point all the class transitions are built up and can be reused, which speeds up the whole process pretty good. The next optimization has to do with the execution of the JavaScript source code. JavaScript is written in plain text, and JavaScript is a scripting engine, which gets interpreted just in time. So the source code is read by the browser and then compiled into bytecode. And yes, JavaScript is a compiled language, but just in time. And then the machine code or the bytecode is kept in the browser engine, and the browser engine works on this bytecode. And as long as you have this bytecode in the engine is able to optimize this code. And the optimizations are in a way that the engine is trying to guess what you're up to. So the engine is patching your source code and is trying to guess what's next. So, for example, I assume you want to access the X property of the point next on. And then the engine patches the code accordingly, and the code gets executed faster. If the guess of the engine is wrong, then the patch is reverted and the original unpatched version of the code is executed. The longer you run the same code in the browser without a reload, the more optimized the code gets. So a new reason to build up single-page applications, because the engine is able to optimize the code even more. So this is an example of how this code might look like. So if you access this property, then the machine code looks in this hidden class, which is pre-generated, and if it's correct, the assumption of the engine, then the optimized code is used. If not, the optimization is reverted and rebuilt. And the more often the cache misses, or the optimization is not correct, the slower your code gets. So you have to reuse the code as good as you can, reuse classes and the same object structures, and then the optimizations are useful. And this is one of the reasons why you should use these class syntax, because then you access the properties in the same order. You access first the X and then the Y, and then you have class C0, C1, C2. And for the next point object, you have the same transition. If you access Y in the first place and then X in the second place and the other way around, the optimization of the engine is not true, because you don't follow the same path, and then the optimization is reverted. And this is true for all the properties as soon as you access them for the first time. And then you can access them in which order you just want to. JavaScript has a garbage collection, but you cannot interact with the garbage collector on your own. You have to keep the memory clean by accessing and leaving variable scopes, which is quite hard, as you soon will learn. But if you use the memory management of JavaScript correctly, it's quite a good thing, because the garbage collector is pretty intelligent, and it uses some optimizations, which we will have a look now, because your application uses memory for objects. And as soon as an object is created, memory is referenced and blocked for this object. And the memory of your JavaScript engine is divided into two sections. You have a young generation storage part and an old generation storage part. The reason for this division of the memory is you have various algorithms to clean up the memory. A very fast one for objects that get created and thrown away, and a slower one that's optimal for a big memory chunk, which is used for objects that reside in the memory for a longer period. And this works just as follows. You create objects which are stored in the yellow section in the new generation, and the new generation is fragmented as well. As soon as one fragment is getting full, objects that are used are being transferred in the next section, and then the section is cleaned up, and everything that is not used is getting thrown away. As soon as you move one object for the second time, the object is transferred into the green section in the old generation, and then another algorithm is used. And in the green section, this is not that fragmented, but all the objects that are used are marked, and all objects that are not used are swept away. So this is called mark and sweep algorithm, and this is taking longer than the algorithm of the yellow portion. So if you want to optimize the memory consumption of JavaScript, try to reuse objects. Try to create an object and then modify the properties of your objects, because then the garbage collector has not that much to do and is faster and more efficient. So the key of a good memory management is reuse things rather than create and throw away. The memory management of JavaScript is taking some time, and the engines are optimized in a way that this memory management is being done in the CPU idle time. So if the CPU has nothing to do, then the garbage collector kicks in. for a very good reason, because if you have a browser game or something with animations, then the animation is calculated and executed. And if the garbage collector kicks in, then the whole process is paused, and then the garbage collector does its work, and then the process of JavaScript and the animating thing is resumed. This means that the animation is paused, the user sees some hiccups, and then the garbage collector continues. If the garbage collection is being done in the idle time of the CPU, so in between the 60 frames per second rate, then there are no hiccups. And this is a further optimization in order to have very smooth animations in the browser. So there is no halting of the whole process, but the garbage collection is fragmented in CPU idle time, and then the animations are okay. So keep in mind that the longer your application runs in the browser, the better it can be optimized. That's the key of the whole thing. So now we are getting back to the visual part of our application. And a problem which occurs when you change parts of your application. Because then the browser has to rebuild the tree structures. So if you change a part of the CSS or the document object model, then the browser has to repaint the thing and recalculate all the nodes that should be displayed. And this is known as repaint and reflow. So if you, for example, if you remove a box in your application, then all the following parts of your application have to be recalculated and reordered, because there is something missing in between. And this takes some time, as you have seen in the beginning. And there are a lot of operations that trigger that kind of layout changes, which are, for example, the addition and removal of elements in your application, but also scrolling. So if you scroll through your application, the browser has to recalculate the layout and the part of the application that is currently displayed. What is even more worse is that if you read some CSS properties, so for example the height or width of a certain element, then the layout is also recalculated, which is not a good thing. So there are a couple of best practices in order to optimize or reduce repaints and reflows. You should not apply layout changes step by step, but group them together and apply them at once. Use CSS classes wherever you can. So if you apply a single style and then a single style again and a single style again, then you end up with 3 recalculations and repaints of your layout. If you group them together in one CSS class, then the browser knows which changes that should be happening, and it optimizes the applying of the changes in the DOM, and it's speeding up. If you have to redo a whole part of your application, then you take out the part of your application from the visible elements of the application, apply the changes, and then reattach the subtree of the DOM. So you cut up a tree or a subtree of the DOM, do the changes, and then attach it back to the DOM, because then you have 2 operations, the removal and the reattachment, and not the single changes in the subtree, which optimizes the process furthermore. To overcome the problem of recalculating the layout when you read a certain CSS property, cache style parts of your application in JavaScript variables. If you do so, you have an access to a JavaScript object and you do not need to recalculate the layout. And the last thing is use fixed positions, because if you position your object in a fixed way, then it doesn't affect any further objects, but only the current one, which is better for the recalculating part of the repaint and the reflow. If you're interested in how long it takes, just open your DevTools and have a look at the green and the violet part of the graphic in here, because then you see when and where the browser is doing layout stuff. And in this flame part of the graphic and the upper one, you see where the changes happen and where you can optimize. You can zoom in to the graphics and see which operation is causing the problem or the potential problem for the performance, and then you can optimize it. So for example, if you do a lot of changes to your layout, then you have certain peaks in recalculate or in rendering and painting, and this is a clear indicator for optimization. If you have a long-running application, then you face memory leaks sooner or later. Memory leak means that the memory of your browser is filled up and not freed anymore by the garbage collector, and that causes the system to become slower and slower, and at some point your application is unresponsive, and that's a big problem. So what is the cause for a memory leak? A global variable. So you should omit global variables in JavaScript, because as soon as you create a global variable, the garbage collection cannot happen for this variable, because it's always referenced. If you're using intervals, so regular occurring functions, they are not freed by the garbage collection as well. And if you forget them and they are executed in the background, they are not freed as well. And they are consuming memory. And a JavaScript function is not consuming only the current scope of the variables, but also the creational context of this function. So all the variables that are valid when the function is created are stored in the scope of this function. So it's consuming more and more memory. If you put in a subtree of the DOM into a JavaScript variable in order to apply changes and then reattach the subtree and forget to free the memory or delete the variable, it consumes also a lot of memory, because it stores all the DOM nodes, all the properties and everything that's needed to recreate the subtree. And if you forget to free the memory, then it's consuming more and more of this memory. And of course, closures, which are functions and their creational context. A very good example of a very nice memory leak is this one here. You have an outer and an inner function and an interval. And you always reference some variables that are not freed. And the result is, so you are creating a string, or you create an array with 10 million, I think, items, and join them by a star, which leads to a very long string. And this string is stored in a variable, and this variable is always referenced by closure scoping. And this leads to this figure. And if you see figures like that, that means you have a big problem, because the memory is consumed up to a certain limit, and then your browser says, I don't want to work anymore, and yeah, your application is dead. How can you overcome those problems? There is a part of your DevTools that is responsible for memory profiling, and you can take a snapshot of the current heap of your JavaScript memory and have a look at which objects are in your memory. And there you get a metric that tells you how much space is consumed by a certain amount of objects. And as soon as this amount gets over the default objects of the browser, you see this and you are able to optimize your problem, because you get the creation point of these objects, and then you can have a look at the part of your application where the memory gets consumed, and then you can free up the memory. In this example, a possible solution would be deleting the variable reference, and then the garbage collector is able to clean up the memory. And then you have a, not this growing memory, but a normal line. I already told you that you might face problems when animating stuff in the browser. JavaScript is not good in animating stuff, because JavaScript is executed in the CPU, and the CPU is not optimized for our animations. If you want to do fancy animations in your application, you should use CSS, because CSS is much better in doing fluent animations than JavaScript would ever be. And the goal is at least 60 frames per second, which is a time to calculate your animation in 16.6 milliseconds, which is not a lot of time. If you this is an example of how to animate in JavaScript, and this involves an interval which is executed in 10 milliseconds, which is below the 16.6 milliseconds, which guarantees you a fluent animation. But the problem is JavaScript is single-threaded. So if you calculate your animation on and on again in 60 milliseconds, or in 10 milliseconds in this case, the JavaScript process is blocked in that time and is not able to do another calculation. And this is a problem. So you should use CSS animations, or there is a new API in your browsers, which is called the Web Animation API, which puts the animation to the GPU, so the graphical processing unit, which is optimized for animations. The downside is the support for the Web Animation API is not that good. So you can use them in Firefox and Chrome and have to use an alternative for Edge and Safari right now. Safari is planning to implement this API, but Microsoft is not. So the better fallback would be CSS animations, and the same animation you saw earlier with the interval and all the stuff is written in CSS in 5 lines, or 6 lines in that case. You define a property and you tell the browser, please animate this in a certain way, in a certain period of time, and that's it. And then it's executed on your graphic card, and then everything's okay. If that's not enough for you, so this is a linear transformation of a certain position information of an element, and if you want to, for example, animate a curve or something, you can use the add keyframes property, which gives you a very fine control of an animation process, and you can tell the process in 1 second you move in this direction, in another second you move in that direction, and you have the complete control over the process. And luckily there are generators for that kind of animation. Just go to, for example, CSS Animate, and then you can drag and drop the animation and get the code and paste them in your application. you can tell your browser if you need a certain resource, for example, an image or an HTML or CSS or something, to preload the stuff in order to overcome the waiting process to load the certain resource. And this is done by prefetching. So you create a link element, and then you tell the browser, dear browser, please fetch these resources. Currently, I do not need them, but if the user moves to this and that resource or activates something, then the resource is needed. So as soon as the browser is idle, it fetches the resources, and if the user navigates to another part of your application, the resource is already loaded in the browser's memory and is displayed instantly. So the last part is have a look at how the others do performance. And a good point to start is how do big frameworks do performance. So for example, how are the developers at Facebook, which are creating the React framework, or the creators of Vue, or the creators of Angular, are handling those problems you're facing on a daily basis. And React is overcoming the problem of the repaint and reflow and the applying of changes to the DOM tree with a very cool solution which is called the virtual DOM. The slowest part in your browser is the creation of the DOM tree, the HTML structure. And the virtual DOM says you have a copy of the DOM tree in the JavaScript part of your application, and you change your application not directly in the DOM, but in the virtual copy of the DOM, and then the framework applies the changes to the DOM in an optimized way. That's just what I told you previously. You detach a certain part of your application, apply the changes, and then reattach them. But they are optimizing this furthermore. And this is executed very fast, to be precise, in this 16.6 milliseconds, so you can have fluent animations even in React, even in JavaScript. And even Vue and Angular in a part is using the same technique or the same pattern in order to perform changes. So they are not applying a change for change, but they are grouping together the changes and apply them at once. And this this algorithm I just mentioned is called reconciliation, and React has different schedulers for this reconciliation. They have a real-time scheduler, which is performing animation-related updates. And as soon as you have server communication, which is not that critical, it doesn't mind if you display data from the server in 16.6 or 32 or something milliseconds. So they are a little bit delayed until the animation is calculated and then the information from the server is displayed. So they are scheduling the time slices based on how critical something is. And a fluent animation is more critical than displaying the response from the server instantly. So they are optimizing based on the best practices I just showed you. So, do you have any questions? No. Okay. So if I get your question correctly, it's related to tabs of the browser. So the limit, these 6 parallel connections are applied to a tab and a resource. So to be precise, the limit is by origin. And a certain origin is the host part of the URL, the port, and the protocol. So you can overcome this limitation if you place, for example, the images into a subdomain. And then you have another 6 parallel requests. And the tabs of your browser are completely independent. So you're not limited over various tabs or various windows. So every tab has its own parallel requests, and they are not limiting each other. So this is not a problem. The limitation is just that a normal browser client is not DOSing a server. Because if you request hundreds of resources in parallel, and if you have hundreds or thousands of parallel client requests on a server, the server would at some point be unresponsive. Okay. Okay, then thanks for listening. And yeah, if you have further questions, I'm here for a couple of at least minutes. So yeah, would be nice if we have a cup of coffee and yeah, have a nice conference and yeah, see you. Bye.